Hey y'all, welcome back. Today we are reviewing for our midterm exam. This is going to cover just about everything that we've talked about in semester one. Our primary focus here is understanding differentiation and a little bit of limits as well, which would make sense since a derivative really is just a limit. But what we've got on the review for you here is just one or two problems from each day that we've been together. So let's just jump into it. I'm not going to spend a lot of time with a little intro or anything. We're just going to get straight into the problems. So the very first day that we were together, we did some review problems, and specifically what you need to know for the midterm is you got to know your trig values pretty decently. So let's just go through how you would evaluate each of those. So I like to think about the unit circle when I'm trying to evaluate these, and there's five key angle measures that you should be pretty well aware of, and that's 0 radians, pi over 2 radians, which is at 90 degrees, pi over 6 radians, which is exactly 30 degrees, pi over 4 radians, which is 45 degrees, and pi over 3 radians, which is 60 degrees. And each point on the unit circle, on the circumference of the unit circle, will have coordinates that correspond to the sine and cosine values of each of these angle measures. So for instance, at 0, this point right here is 1, 0. This point right here is going to be root 3 over 2, 1/2. This point at pi over 4 is root 2 over 2, root 2 over 2. At pi over 3, we've got a coordinate that's 1/2, root 3 over 2. And at pi over 2, we've got a point at 0, 1. And if you're really just confused about how I'm coming up with all those numbers, they all come from our two special right triangles. I'm not going to go into a ton of detail here because we're kind of getting in the weeds. But our 30, 60, 90 triangle has a ratio of x to 2x to x root 3. And then our 45, 45, 90 special right triangle is going to have a ratio of x to x to x root 2. So basically, where all these numbers are coming from are, like, if, for instance, at pi over 4, if I draw a right triangle like right here, I know that the hypotenuse of this circle, because it is the unit circle, is just 1. So like this is 1. And then I can use my right triangle ratios to come up with root 2 over 2 and root 2 over 2. So that's basically like where all that stuff's coming from. I'm not going to spend a ton of time on that. That is a whole lesson in and of itself. And we're just reviewing today. So bottom line is you're going to get these sine and cosine values from the x and y coordinates of these points along the unit circle. So the x coordinates that we see, like pi over 2 is 0, at pi over 3 it's 1/2, and so forth. These will all give you the values for cosine of their corresponding angle measure. So cosine of an angle theta, which is the adjacent side of a right triangle divided by the hypotenuse. Now in all these triangles, the hypotenuse is just going to be 1, so we're just really looking at that adjacent side. And this adjacent side right here is always going to correspond to the x value. So the cosine is going to be the x coordinate of all these points. Similarly, sine, which is the opposite side divided by the hypotenuse, and we're looking at a right triangle, is going to be the y coordinate. Okay, if I look at this, go back to this 45 degree triangle right here, I can see that the opposite side would be this side. It'd be root 2 over 2 divided by 1. It's always going to be divided by 1 because the hypotenuse is always going to be 1 on this unit circle. The radius is always 1. And so this is just going to be the y coordinate from the unit circle. So let me just kind of clean up all this stuff a little bit so we can kind of see where our answers are going to come from on all these. You can also just draw a right triangle and focus on those special right triangles that I drew up above. This can also help you find these values. But if you know your unit circle pretty well, then I think it's a little faster to do it that way. Okay, so let's go through these one at a time. Sine of 0, we're going to look at 0 radians, and we're going to report back the y coordinate. So sine of 0 is 0. Cosine of 0, that's going to be the x coordinate, and so that's just going to be 1. Sine of pi over 6, we can see, sine of pi over 6 is going to be the y-coordinate of pi over 6. That's going to be 1/2. Cosine of pi over 6, similarly, is going to be root 3 over 2. That's the x-coordinate at pi over 6. Pi over 4, both the x and y values are the same, so both sine and cosine are both of pi over 4 are both going to be root 2 over 2. Pi over 3 has a y-coordinate of root 3 over 2 and an x-coordinate of 1/2. So those are our sine and cosine values at that angle measure. And then at pi over 2, the y value is 1 and the x value is 0. So the sine is 1 and the cosine of pi over 2 is 0. So that'll give you the majority of these. The rest of these questions have to do with natural log and exponential expressions. Just know that a natural log is really like log base e. You will never see it written as log base e. You just have to know that's what it means. But when you're trying to evaluate a logarithm, really the question you're asking yourself is, like, if I want log base e of 1 or natural log of 1, the question I should be asking myself is e to what power is 1? And really anything to the 0th power is 1, so this is going to equal 0, and that actually gives us our answer over here. E to the 0th power is 1. Anything to the 0th power is 1, with the one exception of 0, but we don't need to get into that. So natural log of e, again, is going to be like e to what power is e in this case. And so e to the first power is e. So anytime the base and the argument are the same in a logarithm, that will always equal 1. Okay, so that wraps up our day 1. Let's go to day 2, where we talked about limits at infinity, and we went through a bunch of algebraic techniques to find these limits. Now, later on in the year, we learned about L'Hopital's rule that can make some of this algebra a little bit easier if we solve these limits using calculus rather than algebra. But I'm going to focus on the algebra here just so that we can kind of get back into that and refresh ourselves how you would actually find these. So for number 1, we're looking for the limit as x approaches infinity of this expression right here. Anytime you're finding the limit as x approaches infinity, you want to be thinking about horizontal asymptotes. Okay, this is finding the horizontal asymptote. So to find the horizontal asymptotes, if we have a rational function, we really just want to look at the first degree, because this limit will equal the limit as x approaches infinity of 3x cubed over 5x cubed. Those are the largest terms, and by largest I mean the fastest growing terms. So we're really just going to focus on those. And we could see that the x over 3 over x to the third power x cubed over x cubed will reduce to 1. So this is going to equal the limit as x approaches infinity of 3/5. So we just get 3/5. Now, when we were back in pre-calculus and maybe even in Algebra 2, when you first learned about horizontal asymptotes, you learned to divide the leading coefficients when the degrees were the same. So notice we are getting that same answer. You could also solve this one using L'Hopital's rule. We're going to do some more L'Hopital's practice later, so I'm not going to bother with that. But if you were to use L'Hopital's rule on this one, you would get 3/5 as well. Number 2, we've got a square root. Now, whenever you have the square root of like a variable square, this happens every once in a while. We still just really want to focus on those two largest or fastest growing terms on the numerator and the denominator. So in this case, this equals the limit as x approaches infinity of the square root of 16x squared over 3x squared. Now be careful with this square root. This little nuance here really is not going to be that big of a deal for this problem, but in general, you need to be aware of that. That when you take the square root of a square, you actually get let me put this separately, you're going to get the absolute value of 4x, not just 4x. Now, whether or not this is the absolute value, we're going to positive infinity. So if I plug in like a positive number here, this thing's going to be positive. So this is just going to equal the limit as x approaches infinity of 4x over 3x squared. Now, if I reduce one of those x's, if I simplify those and cancel out one of those x's, I'm going to get 4 over 3x. And anytime the denominator is going to grow faster than the numerator, we say that the horizontal asymptote is y equals 0. Therefore, this limit is just 0. Number 3, you could approach this kind of like we did talked about in number 1, where you just look at your largest growing terms, but hang on, wait a minute. This has one where the numerator is growing faster. So this is going to be equal to the limit as x approaches infinity of this ratio right here, negative 2x to the 5th over 3x squared. And I can simplify this a little bit because I can cancel out 2 of these x's. It's going to equal the limit as x approaches infinity of negative 2x cubed over 3. And as x gets bigger and bigger and bigger, this value is going to get bigger and bigger and bigger. However, when we get up to no matter what this is, as long as this is a positive number, and it will be if x is going to infinity, if I multiply that by negative 2, this whole numerator is going to be negative, the bottom is going to be positive, and so this whole limit is going to go to negative infinity. Now, when you write negative infinity, technically the limit does not exist here. You do need to be approaching a specific value in order for a limit to exist, but it is acceptable and encouraged in notation to write either positive or negative infinity if the limit doesn't exist because of that unbounded behavior. So basically, you're just trying to communicate that there is no limit because the function goes to negative infinity. But for shorthand, we can just leave it as negative infinity. And sometimes you'll see some multiple choice options where does not exist is not even an option, where you're forced to choose between positive and negative infinity. And so that's how you make that decision. Just plug in either, if it's going to positive infinity, plug in some large number into x and evaluate whether or not it's going to be positive or negative. And if it's going to negative infinity, you could plug in some large negative number, I guess technically a small number, but like negative 1,000,000 or something like that, and try to figure out whether or not the overall fraction is going up to infinity or negative infinity. So there's number 3. Let's move on to day 3. Taking a look at this graph and trying to evaluate some limits graphically. So first, let's take a look at part A. It says, what's the limit as x approaches negative 3 of sine of f of x? Hold up. Let's back this up a little bit. Of sine of f of x. Now, usually when you have a composite function that you're trying to evaluate, you just evaluate from the inside out. But I do want you to know that when you do have a limit of a composite, you can rewrite this as, in this case, sine, or whatever the outside function is, of the limit of the inside. And if you think about it this way, I think it makes the problem a lot easier, because now we're just evaluating the limit as x approaches negative 3 of the function in the graph, and then we'll take the sine of that. So if we look at where x is 3, or negative 3, sorry, that's going to be, let's see, negative 1, negative 2, negative 3 is right. This is where x is negative 3. I'm going to use a different color there to make this a little easier to look at. The limit as x approaches negative 3 is going to be equal to the left-hand limit and the right-hand limit, assuming they're the same. And sure enough, if we check the left-hand limit and the right-hand limit, the value of the limit overall is equal, and it is equal to, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is just going to equal sine of 9. This is going to be irrational. We don't need to simplify it any further. Let's just go ahead and leave it as sine of 9. Part B says, what's the limit as x approaches 2 with a little plus on here? And this little plus means from the right, from x equals positive infinity, okay? So you can think about it as being from positive infinity or just like from the right. So if you are sort of reading this graph from the right, let me kind of explain what I mean there. Let's say we have a vertical line that's showing us like what x values we're actually looking at. Can I make a vertical line here? Let's see if I can actually do that. Nope, that's not going to look good. Yeah, that's close enough. So basically what I'm saying is if you read this graph from right to left, okay, and let your eyes follow the value of the function here. As we get closer to x equals 2, which I'll stop here, okay, the value that the function is approaching from the left, and that's kind of the important part here. I'm sorry, from the right, and that's the important part here. From the right-hand side of the graph, our function is approaching this value right here, which is negative 2. So yeah, this one's going to be equal to negative 2. Part C wants the value of the function of at x equals at x equals positive 2. And basically, we're just going to be looking here. This is where x is 2. So the value of the function, you're going to report back that closed dot here. That indicates that the function is defined there. So this one's also going to be equal to negative 2. All right, now we want to find some more limits algebraically. So before we were looking at those limits to infinity, here x is not going to infinity, it's going to a specific number. This is another case where if you plug in, if you use direct substitution here, and you get 0 over 0, you can use L'Hopital's rule. And I think on these, I might even go into how you might do that. So first, let me show you how you would solve these limits algebraically, and then we'll get into how you would solve them with calculus. So algebraically, if you've got a setup here where you've got a square root, and then either plus or minus another term, that's usually an indication that you want to multiply both the top and the bottom by the conjugate of whichever side has that square root. So we'll multiply this by root 2x plus 1 plus 3 on both the top and the bottom here. Okay, so when I do that, the roots, this times this, these two square roots are going to multiply together and just leave you with 2x plus 1. When I multiply these outside terms and the inside terms, those are going to cancel each other out because you're going to have 3 times the root minus 3 times the root, and that'll just be 0. And so the last multiplication to do is this negative 3 times 3, which would be negative 9. Now the denominator, I'm not even going to mess with. What I'm trying to do here, my whole goal is to cancel out that x minus 4 so that I can successfully use direct substitution. And so you can see how that numerator is going to simplify. 1 minus 8 is negative 8. So you have 2x minus 8 on the top. Everything else on the bottom will remain the same. But I can factor out a 2 in that numerator. So I get x minus 4 over x minus 4 times that expression with the square root. And now I can reduce that x minus 4. That was kind of the whole point of doing the conjugate thing. Those cancel out. So this is going to equal the limit as x approaches 4 of 2 over the square root of 2x plus 1 plus 3. And now you might be able to see at this point that you can go ahead and use direct substitution, plug in that 4 into x, and this will equal 2 divided by the square root of 2 times 4 plus 1 plus 3. Make a note here. This is something that most everyone is still struggling with, is like when to write limit and when not. Notice that I'm not writing limit anymore. And you stop writing the limit as soon as you do that direct substitution. As soon as you plug in the value and you start evaluating, no longer do you need that limit notation. So yeah, this is just going to be 2 over the square root of 9 is 3, and 3 plus 3 is 6. So this is going to equal 1/3. Now, I said before that you could use L'Hopital's rule on this one, and you definitely could. You would just need to find the derivative of the top, find the derivative of the bottom, and then try to plug in 4. And that's going to work out pretty nicely here. I'll show you out to the side here that you could use that strategy. So you could say that this equals the limit as x approaches 4 of, what would that be, 1/2 times 2x plus 1 to the negative 1/2. All over 1, the derivative of x minus 4 is just 1. And so if I plug in 4, this is going to be, and I'll kind of skip some steps here because we already solved this one out, but it's going to be 1 over, oops, need to use chain rule. Don't forget about that chain rule, times 2. So even, this actually works out even nicer than I thought, because the 1/2 times 2 is just going to be 1, and so those are going to reduce. And so really all I have here is 1 over the square root of 2x plus 1, and I did not include my limit, just got done talking about that. Got to be careful here. But now I can go ahead and plug in 4. Okay, this is going to be 1 over the square root of 2 times 4 is 8 plus 1 is 3. So this is just going to be 1/3. Notice how you get the same answer. So you could use L'Hopital's rule, or you could use the conjugates to find that answer. Number 6, I'm not going to, well, I guess maybe I could do both here. Here we just want to really factor. So this is going to equal the limit as x approaches 4 of negative 3 times x minus 4 over x plus 3 times x minus 4. So the x minus 4s are going to reduce. And that really only works with these limits here. The limit as x approaches 4 of negative 3 over x plus 3. Now I can substitute in that 4. So I'm going to get negative 3 over 4 plus 3 is 7. So I get negative 3 over 7, and that's my answer. Now this one is not so bad as long as your factoring skills are decent. But once again, we could use L'Hopital's rule here. So if I were to use L'Hopital's rule, just show you how this would work separately. This would equal the limit as x approaches 4 of negative 3 over 2x minus 1. And then if I substitute in 4, I'm going to get negative 3 over 7 again. So you get the same answer. And hopefully you're seeing that L'Hopital's rule is pretty useful. But you want to be careful. You don't want to overuse it. I think the optimal times to use it is when you try to use direct substitution, you get 0 over 0. You can only use L'Hopital's rule if your limit is indeterminate when you use direct substitution. So if you get 0 over 0 or infinity over infinity or some kind of variation like that, that's when you're going to use L'Hopital's rule. Or when you could, I should say. As we're seeing here, there are also algebraic means to get those limits. Okay, moving on to day 5. It says use the table to answer these questions, and we can see that we have various values of x and then value for f of x, and these are all going to be limit questions, so it's really just about understanding what the notation means. So this first one, let's zoom back out here. Where were we? There we are. For this first one, we're going to find the limit as x approaches 2, but we're going to find the limit as x approaches 2 from the right. Okay, so maybe I'll make that green. We're also going to find what it is from the left. I'll make that red. And then if those two things are equal, then that's going to be the value of our limit overall. So as we look at the values for f of x, you can see if we're approaching from the left, from negative infinity, we don't really care what's happening at 2. We just want to know what is the value approaching. And you can see that as we approach from the left, the y values are getting closer and closer to 4. However, if we approach 2 from the right, okay, so we're going this way. So this is from the left in red, and the green is from the right. From the right, our y values are getting closer and closer to 5. Notice how these are not the same, right? 5 does not equal 4. So since 5 does not equal 4, we can say that the limit as x approaches 2 does not exist. Okay, those two numbers have to be the same. Now, the value of the function at x equals 2 is just simply the y value that we can see right here is going to be 6. Day 6. Okay, so here, this is like the only, I think, kind of tricky limit where you really are not going to use algebra or calculus, but rather arithmetic. So here, when you try to use direct substitution and you try to plug in that x equals 4, you're going to get 20 over 0. And that's no good, right? That's undefined. But it's not 0 over 0. So we can't use L'Hopital's rule. And so instead, we have to think about what is happening around the graph at x equals 4. Now, if we try to do direct substitution, like I said, we do get a divide by 0 error, but we know there's not going to be a hole. There's no removable discontinuity because it doesn't make the numerator 0 also. And so what's happening at x equals 4 is we have a vertical asymptote. Okay, vertical asymptote is a non-removable discontinuity. And really what you need to know is whether the function is going up or going down on either side. Now, we haven't really decided which one it is, but let's check. So in other words, we want to find really what's going on with the function on the left-hand side and the right-hand side. If they're both going the same direction, then we can say that the limit is either positive or negative infinity, depending which direction they're going. But if they're going in opposite directions, we'll say does not exist. So if we plug in a function, a value like, so we're just going to test a couple of values. Let's test 3.9 and we'll test 4.1. So if we test 3.9, which would be just to the left of x equals 4, and we plug that in here and here, I don't really care exactly what it equals. I just want to know if it's positive or negative to see if the function's going up or down. So if I plug in 3.9, I'm going to get a positive in the numerator and I'll get a positive in the denominator. So that means that on the left-hand side, my function is going up. Okay, we're going this way, not that down. Okay, and then if I plug in 4.1, I get 5 times 4.1 on the numerator. That's going to be positive. If I plug in 4.1 in the denominator, I'm also getting something that's positive. So that means that the graph on the right-hand side is going up to positive infinity as well, not down. So this is basically what's happening around x equals 4, at least very close to it. We don't need to analyze the function anywhere like further away from it. So we can write our answer here that the limit is going to be, there really is no limit. From a technical standpoint, the limit doesn't exist due to that unbounded behavior. But because on both sides we're going to positive infinity, it is okay to say that we're going to infinity. All right, then we talked about continuity, and this is the same graph that we were given in problem 4. So we're going to just analyze this a little bit further. It says we have a jump discontinuity. A jump discontinuity is where you have a jump from one point to the next, and these points might be filled in, they may not be. They can't both be, but it doesn't really matter to answer this question. We just want to know, where's that jump discontinuity? And we can see that jump discontinuity is occurring right here at x equals 2. This is a non-removable discontinuity. It falls in the same category as the vertical asymptotes, and that's because the limit does not exist there. Okay, that's really the big difference between a removable and a non-removable discontinuity. For a removable discontinuity, the limit exists. Okay, so typically when you have a removable discontinuity, it will look like a hole in the graph. And so this is asking for where does that happen. We can see that's going on right here. So as long as we count correctly, we should get the answer right. -1, -2 at x equals -3. Okay, the day after that, we reviewed for our test. So this is just going to be kind of a random question from that review. And this is going to be about continuity again. It says, find the value of k that makes the limit as x approaches 2 of f of x exist. So in order for that to exist, the left and the right-hand limits have to be equal. So basically what we're looking for on this piecewise function is we got y is x plus, sorry, let me say that again. When x is less than or equal to 2, we've got this square root function. And then when x is greater than 2, we've got this quadratic. And what we want is for those two pieces to match up to each other and be equal when x is 2. So we're going to set each piece equal to each other. So the square root of x plus 7 equals x squared minus x plus k. And we're going to substitute in 1 for x. So we're going to have 1 plus 7 equals 1 squared minus 1 plus k. Well, here we're going to have, not 1. I'm sorry. Let's back that up. Let's fix that at 2. I don't know why I was thinking 1. There we go, 2. All right, so the square root of 2 plus 7 will just be 3. And then here we've got 2 squared is 4. 4 minus 2 is 2. So if 3 equals 2 plus k, so k has to be 1. Yep. All right, and then we took our test. So here's a couple questions that were from that test. Determine the horizontal asymptotes for each of the following. Another way I could ask this question is to find the limit as x approaches infinity of f of x. This is basically the same question. It's just that sometimes you have multiple horizontal asymptotes when you have that square root thing going on. Here, we're not going to have multiple horizontal asymptotes, so we're just going to approach it rather traditionally. So the first one, we're going to look at the basically the leading terms here. So the numerator is leading term. It's not written in standard form, so we have to find it, is 2x cubed. The one in the denominator is 5x cubed. And so when we look at those leading terms, you see that their degrees are the same. So that means the horizontal asymptote is going to be the ratio of the leading coefficients. So our horizontal asymptote is going to be 2/5. This would also be the answer to the question, what's the limit as x approaches infinity of here? That's really what a horizontal asymptote is, by the way. Horizontal asymptote is the limit as x approaches infinity. Part B, we're going to approach very similarly. Take a look at the leading term on the top is this negative 4x squared. Leading term on the bottom is going to be x cubed. And anytime the leading term on the denominator grows faster than the numerator, meaning like if it's rational function here, we're going to look at those degrees. If the degree is larger, then the horizontal asymptote is always going to be 0. Okay, this kind of led us into our second unit, where we started actually talking about derivatives. It's been a long time since we first introduced derivatives, but the definition of a derivative is really, well, a derivative is a limit, okay? Specifically, a derivative f of x is going to equal the limit as h approaches 0 of f of x plus h minus f of x over h. And so we're not going to have a full-on discussion on why this is the definition. You can go back and go back to our lecture video on that particular day to get more details. But whenever you see a problem like this, I mean, this problem has shown up so often, not this exact one, but one like this. It was even in our last Unit 4 test. Anytime you see this limit, even if it's mixed up with some other limits, if you ever see this h approaches 0, that is going to be a sort of like should be an alarm in your head. Say, hey, wait a minute, that is not really a limit question. I mean, technically, I guess it is, but the way you want to approach this is not to try to solve it as a limit, but rather try to solve it as a derivative. All you need to do is be able to recognize what are you actually trying to differentiate. So that's always going to be this function right here. Remember, that's the derivative of f of x. So if we look at this piece right here, this whole limit is going to equal the derivative of e to the sine x. Now, you do have to know a little chain rule to differentiate this, but that's what this thing equals. Okay, so let's go ahead and find that derivative. The derivative of e to the x is just e to the x, but I do need to use chain rule here, so I have to multiply by the derivative of sine, which is cosine. So we get e to the sine x times cosine x. These limits can be a little intimidating, especially if it's just kind of like snuck in, like if it's like mixed in with a bunch of other limits that are not, limit definition of the derivative. You might get a little confused on how you should approach it, but just be on the lookout for that, especially with this h approaches 0. That's kind of the giveaway, especially on the AP test. I think they do that a lot. So, yeah, that's the answer to number 12. For number 13, we're just finding the derivative. And so we're just going to differentiate each term separately here. And this one's not too bad. You just have to remember how to deal with these like monomial denominator terms and also ones that have roots here. I'm going to rewrite both of those as powers of x. So that first term I'm going to rewrite as 3x to the negative second. The second term I'll rewrite as 2 times x to the 3/5. And I won't modify the rest here. And the reason why I'm rewriting those first two terms is so that I can just use the power rule directly and not have to worry about like quotient rule in that first term or anything like that. So y prime is going to be negative 6 x cubed, or x to the negative 3, not x cubed, but x to the negative third power, plus, here we have 3/5 times 2, that's going to be 6/5. And 3/5 minus 1 would be like 3/5 minus 5/5, so that'd be negative 2/5. The rest of these terms are going to be pretty straightforward. 3 times 8 is 32, so we get 32x cubed, and then minus 4. And that's going to be it. We're not going to simplify any further or rewrite it or nothing. That is going to be our derivative. Okay, number 14 says, for what values of x is the slope of the line tangent to this equal to 8? So let's first find an expression for the slope of the line tangent to this. So let's the slope will be determined by the derivative. So y prime is going to equal 3 times 1/3 is just 1. So this is just going to be x squared. So yeah, x squared, let me clean that up a little bit. X squared plus 2x minus 7. And it's saying what values of x is the derivative equal to 8. So all we need to do is just set this thing equal to 8, and we're going to solve this remaining quadratic. So subtract 8 from both sides, because whenever you solve a quadratic, you always want it equal to 0. Okay, so now we get this. This is a factorable quadratic, and it'll factor as x plus 3 times x minus 3. And then we could set each one of these equal to 0. Using the zero product property, we'll get x equals -5 and x equals 3. These are going to be your two solutions. There's going to be two answers here. So at both of those x values, the slope of the line tangent to this curve is going to be equal to 8. Number 15, given this wonky equation for y, determine the derivative. So yeah, this is back when we were first learning about these trig derivatives, and you still need to know them. So we'll just go through this together. So first, y prime, which is going to be equal to dy dx. At the end of the day, I don't really care which notation you use. Use the one that you like better, but you still need to know that they're the same thing. So the derivative of sine is cosine, so we're going to get 4 cosine x. The derivative of cosine is negative sine, so we'll have -2 sine x. The derivative of natural log of x is just 1 over x, so this will be plus 8 over x. And then the derivative of e to the x is just itself, so this is going to be minus 7e to the x. And there you go. That's all there is to that one. Number 16, we're given a function for h, and we're given a couple of points that are on f to determine the following. And this is going to be an application of the product rule, which is how you differentiate a product. So here are my two functions here. So h prime of x will be the derivative of the first, which is 3 times 3 is 9, 9x squared times f of x, plus 3x cubed times the derivative of f of x. Okay. Yeah, that's it. I guess that's what we could write here. There's not a whole lot to that. We don't need to simplify that or anything. You could simplify it, I suppose. You could factor out a 3x squared if you feel so inclined. That 3x squared might be factored out as a GCF if this were a multiple choice question, but let's not concern ourselves with that at the moment, because really we want to find h prime of 2. So we're going to substitute it in 2 here. So h prime of 2 is going to be 9 times 2 squared times f of 2 plus 3 times 2 cubed times f prime of 2. Now the f of 2 and the f prime of 2, both of those are given to you up here. So you don't have to calculate them out separately. In fact, they don't give you f, so you wouldn't be able to do that anyway, even if you really wanted to. So I'm just going to move this up to give myself a little bit more space here. So h prime of 2 is going to be 9 times 4 times f of 2 is 3, plus 3 times 8 times f prime of 2 is -1. So let's see here. We've got 9 times, which way should we do this? 9 times 4 is, what would that be? 9 times 4 is 36. 36 times 3 is going to be 108. And then we have minus 24. So 108 minus 24 is going to be 84. So h prime of 2 is 84. Number 17 says, given that g of x is e to the x over 3x plus 1, determine the equation of the tangent line. Anytime you're asked to determine the equation of the tangent line, I want you to have your information ready to go. You've got a point, you've got a slope, and you've got an equation you need to fill in. Y minus y1 equals m times x minus x1. I don't care what else is going with the problem. If you see that little phrase, and that's what the question is asking for you, is an equation of a tangent line, I want you to just kind of ignore everything else, get this set up so that you have some direction on how to start this problem. Because you will for sure get a problem where I'm asking you for a tangent line. On this midterm or on the AP test, this is an extremely common question type. So let's just get ready for it. So the point is going to be at 0, something. They give us our x value here. And the slope, we don't know that. So first, let's find the y value. So g of 0 is going to be e to the 0 over 3 times 0 plus 1. We know e to the 0 is 1. 3 times 0 is 0 plus 1. So this is just 1. So my y-coordinate here is going to be 1. The slope will be given by the derivative of g. So g prime of x is going to be, we got to do quotient rule here. Okay, so we're going to use the quotient rule, which is going to be the derivative of the top, which is just e to the x, times the denominator, 3x plus 1, minus the top minus the derivative of the bottom, which is just 3, divided by the bottom squared, 3x plus 1 squared. And so what we really need is the slope when x is 0. So we're going to have e to the 0 times 0 plus 1 is 1, minus e to the 0 times 3 over 3 times 0 is 0 plus 1 squared. That's just going to be 1. So this is going to equal 1 minus 3, which is negative 2. So our slope of the tangent line at x equals 0 is negative 2. And now we have all the information we need to actually write our equation. So our equation is going to be y minus 1 equals negative 2 times x. And I'm going to leave that minus 0 there. You really don't, it's not 100% necessary. But I think if you're just like, get in the habit of writing the point slope form, just like with all the pieces there, even if you don't technically need them, like if your slope is 1, just go ahead and write a 1 there. It's not going to hurt anything. In fact, you'll probably be more likely to get it right if that's how you set it up. So again, you don't necessarily need that minus 0, but I would suggest you probably go ahead and write it. Okay, moving on with these transcendental derivatives, in particular the trig derivatives. These are going to be a little bit more advanced, a little harder to remember, but we've been working with them a lot, so hopefully you have these memorized. We're just looking for the derivative here, so this is just mostly going to be knowing your trig derivatives. So the derivative of tangent x is secant squared x, so we have 3 times secant squared x, plus the derivative of cosecant, which is cosecant times tangent. I take that back. It's negative cosecant times cotangent. So this is actually going to be minus 2 cosecant x times cotangent x. No chain rule or anything, just making sure you know those derivatives. Number 19 says, given the position of an object, and we're given an equation for the position. Sometimes you'll see it p, sometimes you'll see it x like it is here. Sometimes you see it as s for some reason. I don't know if that's like a language thing or something. I've seen the position function given as s before. So just, it might be whatever. In this case, it's x, but it says for what values of t is the object stopped. So when your object is stopped, what that means is that the velocity is 0. Now, what I really want to emphasize here is I want you to write the relationship between the position and the velocity. We saw when we worked out that AP free response question that one of the points was for simply making that connection. And you did not get the point if you did not make the connection, even if you knew it, and you kind of have to know it to answer further questions about this. But we want to make sure we make that statement that the velocity is the derivative of the position. We want to basically make this claim at the very beginning. So anyway, so the velocity, which is the derivative of the position, is going to be 6t minus 12. And so if we want to know when it stopped, we're going to set that expression equal to 0. So we get minus 12 equals 0. And then, we're going to add 12 to both sides, divide both sides by 6, and we get t equals 2. Let's fix that box up a little bit. So we get it stopped at time equals 2. Number 20 says determine the slope of the line normal. All right, normal line. Normally, usually we find tangent lines, but here we're finding a normal line. So the normal line is perpendicular to the tangent line. Just a little vocabulary you don't want to forget about. So we want to first find the tangent line, or at least the slope of the tangent line, and then we can use that slope to find the slope of the normal line. And since they're perpendicular, what we'll do is we'll negate and reciprocate whatever we get for the slope of the tangent line. So let's find the slope of the tangent line. To do that, we're going to find the derivative of y. Okay, actually, before I do that, I'm going to rewrite y so that I can just use power rule here. 2 times x to the 1/3 power. Now I can use power rule. So 2 times x to the 1/3 is going to be 2/3 times x to the negative 2/3. And so that'd be y prime, sorry. And so if we want y prime at 8, I don't really like that notation, but sometimes you'll see it with a little bar here. At x equals 8, that's going to be 2/3 times 8 to the negative 2/3. So really this will be 2/3 times 1/4, which equals 1/6. Okay, so 1/6 is the slope of the tangent line. Slope of the tangent line. And what we want is the normal line. So the slope of the normal line is -6/1. Okay, it's going to be the opposite reciprocal of the slope of the tangent line. Number 21. Given that f is x to the 5th times sine x, find the second derivative. So we're going to do some serious differentiation here. You can see we're going to have to use product rule, at least for that first derivative, and then we'll kind of see how it plays out after that. So let's first find the first derivative, f prime. Derivative of x to the 5th is going to be 5x to the 4th times sine x plus x to the 5th times the derivative of sine x, which is cosine x. So that's our first derivative. That one's not too bad. But now we got to find the second derivative. So we're actually going to use product rule twice. Okay, so the second derivative, first I'm just going to, here's what I'll do to make this a little bit easier to follow here. I'll do the first product rule in green, and I'll do the second product rule in blue, so you can see exactly where all these values are coming from. So for that first product rule, derivative of 5x to the 4th is going to be 20x cubed, then times sine x, plus 5x to the 4th times the derivative of sine x, which is cosine x. So all that is coming from the first product rule off of that 5x to the 4th times sine x. Then we are going to have plus, and we're going to do product rule again for the stuff that I've got underlined in blue. Derivative of x to the 5th is 5x to the 4th times cosine x plus x to the 5th times, it's really would be like negative sine x. And if you want to leave it like this, that's fine. Make sure you have the parentheses so it doesn't look like you're subtracting. But to be on the safe side, I would just rewrite this plus over here as a minus, and then you don't have to worry about it. And there you go. Here's your answer for 21. Number 22. So this takes us up to the very end of the first quarter. This is going to be off of the second test. So the function g is defined by this equation here, where b is a constant. If the line tangent to the graph of g at x equals -1 is parallel to the line that contains these 2 points, what's the value of b? Okay, so there's a lot going on here. Let's try to see if we can make sense of this. First of all, if the line tangent to the graph is parallel to the line that has these 2 points, that means that the slope, since parallel lines have the same slope, will be equal to the slope between these 2 points. So my change in y is going to be 6, my change in x is 3, so my slope is 2. Okay, anyway, let's go back to what this was actually asking. What's the value of b? It says that if the line tangent to the graph at x equals -1 is parallel, what's the value of b? So let's go and, now that we have the slope, we can come up with an equation for the slope of g of x. In other words, find the derivative. So the derivative of g of x is going to be 2x plus b. Now take a look. The slope has to be 2 at x equals -1. So this is what we're going to find. This is how we're going to find b. We know that the slope is 2, so the derivative is 2. The x value is -1, so we can substitute that in here, and we're going to use that to solve for b here. So 2 equals -2 plus b, and if I add 2 to both sides, I'm going to get b equals 4. Okay, so that about wraps it up for the first quarter. And now we're going to move into quarter 2, where we started with the chain rule and did a lot of graph analysis and curve sketching. Number 23 says, what is the slope of the line? Again, normal to the curve. Be ready for that normal, okay? That's going to be perpendicular to the tangent line. Once again, like we saw, what was that? Saw that back on number 20. Okay, so we talked a little bit about that back there. But basically a line that is, the normal line is going to be perpendicular to the tangent line. So you usually got to find that tangent line first, and then, or at least the slope of it, and then use that to find the slope of the normal line. So first we need to find the derivative of h of x. And to do that, I'm going to rewrite h of x with a power of 1/2. And we need to use the chain rule here. So when you use the chain rule, you're going to find the derivative of the outside function, which in this case is something to the 1/2 power. Okay, that's something to the 1/2 power. You can differentiate that using the power rule and bring that power down with 1/2, and then subtract 1 from the exponent. So that'd be to the -1/2. Now, the chain rule says that when you do that derivative, but then you have to multiply by the derivative of the inside. So we're going to multiply by this expression here. Or not that expression, but by the derivative of that, sorry. So times 15x squared times 15x squared minus 2. Okay, so there's h prime. We want to find the slope of this when x is 1. That's not going to be our final answer, but that will help us find the slope of the line that is normal to that curve. So let's find the slope at x equals 1. So that'd be 1/2 times 5 minus 2 plus 1 to the -1/2 power times 15 minus 2. We can simplify that a little bit here. 1/2 times, and here we've got 5 minus 2, that's 3 plus 1 is 4. So that's times 1 over the square root of 4. And that's how I'm dealing with that -1/2 powers. It's 1 over the square root of whatever's inside the parentheses. Times 13. So we have 1/2 times 1/2 times 13. That's going to be 13/4. Now this right here, that's the slope of the tangent line. Okay, so the slope of the normal line, let me bring that down just to, you know what? I'm just going to rewrite that over here. The slope of the normal line will be the opposite reciprocal of this, because the normal line is perpendicular to the tangent line. So the slope of the normal line will be -4/13. Number 24, some more chain rule practice. Here we're trying to find the second derivative. So that notation, really, it might be written like this, or it might be written like this, but it basically means the same thing, which is the second derivative. So let's find the first derivative first. We're going to use chain rule. So the derivative of sine is cosine. So you have cosine of x cubed times the derivative of x cubed, which is 3x squared. So that's the first derivative, and I need a little derivative mark here. In fact, let me stick with the notation that's given here. So this is dy dx. It's the same thing, but just trying to be consistent here. So if I want the second derivative, I'm going to have to use the product rule. Okay, I've got two functions here that are being multiplied. So I'm going to use the product rule here. The derivative of cosine is negative sine. So I've got negative sine of x cubed. Using the chain rule, I've got to multiply by 3x. Okay, that's just simply the derivative of this so far. Okay, times 3x squared. Oh, I'm sorry. No. Oh, wait. Let me back up a second. Times, no, I was right. Times 3x squared plus, so that's our f prime times g, if you're thinking about it like that, plus f times g prime. So plus cosine of x cubed times the derivative of x cubed. No. Gosh, sometimes when you're trying to talk while you're writing it, you can get a little mixed up. I apologize for that. This is all good. Times the derivative of 3x squared, which would be times 6x. So, so this, am I missing something? I feel like I'm missing something. No, I guess that's pretty much it. So this is going to be our derivative. Yeah, sometimes I just, as I'm talking through these, I kind of second guess myself pretty frequently here. You could simplify this a little bit, I suppose. You've got this. Oh, am I missing a square there? Yes, I am. There should be a square here. So you could simplify this a little bit. This could be like negative 9x to the fourth times sine of x cubed plus 6. I mean, there's not really much you can do to simplify this. It might be a little bit more simplified, but that's going to be your answer there. Okay, number 25. G is a differentiable function. So that G is negative. So that means G is below the x-axis. Don't know if that's going to be relevant here, but probably. So G is below the x-axis. Okay, and f prime is given here. Determine the intervals on which f is increasing. Okay, so f is going to be increasing anytime the first derivative is going to be positive. Okay, f is increasing means that f prime is positive, and that's actually going to be our justification. So we need to find f prime, which is actually over here, and figure out when is that positive. So let's factor that f prime out. So f prime is going to be x minus 4 times x plus 3. And then all we really care about, since we just want to determine where f prime is positive, g we don't know too much about, but we know it's always negative. So it's just times like some negative number. I'm just going to put it like that. It's a little unconventional here, but what we want to do is we want to create a number line for f prime, and since we're looking for where it's increasing, we want to know when f prime is positive. Now to do that, we're going to find first our critical values to know when f prime changes sign. And those critical values are going to be places where the first derivative is 0. So if we want to find those critical values, we can see that one of them is going to be at 4 and one of them is going to be at negative 3. So on our number line, we're going to put negative 3, we're going to put 4, and now we can start testing values to see whether or not f prime is positive or negative in those intervals. So if I plug in a number like negative 4, I'm going to get a negative times a negative times a negative, which altogether would be negative. If I plug in a number like 0, I'm going to get a negative times a negative, which is positive. And then if I plug in a number like 10, I get a positive times a negative, which is negative. So f prime is increasing on this interval. So I can say f of x is increasing on the interval negative 3 to 4. And here it doesn't really matter if you use parentheses or brackets, but it's on that interval. And the justification here is because f prime is positive. Okay, so I guess an easier way to say it is just f prime is greater than 0 on that interval on negative 3 to 4. And this is why I kind of like using parentheses. Again, it doesn't really matter. I'm kind of a stickler for the parentheses here because, it's not actually going to be equal to 0 on the endpoints there. So, yeah, I think this is probably a better way of saying it. Okay, number 26. On this problem, we're given a graph of f prime, and just make sure that you're very clear that this is f prime. This is not f. So part A says, on which intervals is f increasing? So f will be increasing when f prime is positive. And so if I look on my graph of f prime, I'm just looking for the interval where the graph is above the x-axis. So this little interval is where f prime is positive. Also, we've got a little one over here. So yeah, the answer to our question is going to be on the intervals from, let's fix that, 2 to 4 and from 6 to 7. And our justification is because f prime is positive. Part B says, for what value of x does f of x have a relative maximum? A relative maximum on f is where you have like a high point, like on a hill. And this happens whenever the slope changes from being positive to negative. So what we're looking for is for f prime to change from being positive to being negative. And we see that happening at x equals 4, right? So at x equals 4, we have a positive f prime value followed by a negative f prime value. So at this point right here at 4, that's where the f prime is changing from being positive to negative. And that's what's causing that relative maximum on f. So f has a relative maximum at x equals 4, okay? And that's because f prime went from being positive to negative. Part C says, on what intervals is f concave up? So f being concave up means that the second derivative is positive. The second derivative is going to be positive anytime f prime has a positive slope. So in other words, where is f prime increasing? So we're looking for where it has a positive slope. And yeah, let me highlight that in yellow here. I know the highlighting is kind of getting all over the place, but this graph of f prime has a positive slope between 1 and 3 and also between 5 and 7. So these are the intervals where f would be concave up. So you'd say on the intervals between 1 to 3 and from 5 to 7. Okay, and the reason for that, our justification, is because you could either say, well, really we don't really want to reference f double prime because we're not given that, but we want to say f prime is increasing, or if you want to be even more specific, you could say f prime has a positive slope. Either one of these justifications is probably going to be okay. But you want to communicate the idea. You could say f double prime is positive, but since we don't really have any information about f double prime, I don't think that is really the ideal justification here. Number 27, we're given a function, f of x, and we want to determine where the function's concave up. Okay, so this will be kind of similar to determining whether or what intervals f is increasing or decreasing. But instead of checking the first derivative, we're going to check the second derivative. That's where we're looking for the concavity. Okay, f of x will be concave up when f double prime is positive. Sorry about the bell there. Where f double prime is positive. So we need to find f double prime. So let's first find f prime. It's going to be 3x squared minus 12x. Okay, we're going to find where it's concave up and concave down by creating a sign chart. We're going to find the subcritical. Oh, wait, we haven't found f double prime yet. I'm sorry. That would be 6x minus 12. So on our sign chart, we're looking for the subcritical values, which is where the second derivative is equal to 0, and there's only one of them. It's going to be at x equals 2. So if there is a point of inflection then it's going to happen at x equals 2. You only have a point of inflection if you have a sign change here. So if there's no sign change, there's no point of inflection. Now, this isn't asking for a point of inflection, but you'd go through the same process. And what we're looking for here is where f double prime is positive. So we can go back to where we found the function rule for f double prime and just substitute in any candidate or any representatives from either of these two intervals. So like if I want to find the sign of f double prime on this first interval, I'm going to plug in a number like, say, 0, and 6 times 0 minus 12 is going to be negative. So I know f double prime is negative in that interval. And then if I plug in a number like 10, 6 times 10 plus 12 is going to be positive. So I know f double prime is positive here. And since f double prime is positive between 2 and infinity, that means that between 2 and infinity, f is concave up. Okay, so that's our interval, and the reason is because f double prime is positive on that interval. Number 28 says use the values in the chart to find the derivative of f of g of x squared when x equals 2. Okay, so we've got some serious chain rule action going here, but we've got like 3 embedded functions. So yeah, this thing right here is going to equal, first we're going to find the derivative of the outside function, and we've got 3 nested functions here. We've got f, we've got g, and then on the very inside we've got this x squared. So the derivative of f is just f prime, right? So we've f prime, f prime of everything that was previously inside there, g of x squared, okay, times the derivative of the inside. So the inside, the next one would be this green one. So the derivative of that g of something is just going to be, well, the derivative of g of that something. And then lastly, we're going to find the derivative of the inside function. So the derivative of x squared is just 2x. So I'm going to go back and highlight each one of these pieces so you can see exactly like where they're coming from. If that helps, I don't know, but hopefully it helps a little bit. Okay, we just have a triple chain rule function going here. Okay, so now we can just evaluate. So yeah, when x equals 2, we're going to substitute that in here. So we've got f prime of g of 2 squared times g prime of 2 squared times 2 times 2. So I don't really want those equal there. I want an equals here, though. So we've got f prime of, let's see, g of 4. We'll go back and evaluate that later. Times g prime of 4. We'll evaluate that later. Times an extra 4 here. So now we can use the table to simplify this a little bit. Continue on over here. F prime of g of 4. Well, g of 4 is 1. So we got f prime of 1 times g prime of 4 is going to be negative 1/2. Negative 1/2. Yeah, so just negative 1/2. And then times 4. So the last thing to evaluate here is that f prime of 1, which we can find right here, it's going to be 2/3. So this thing's going to equal 2/3 times negative 1/2 times 4, and that's going to be negative 4/3. Number 29 says determine the equation of the line tangent to the graph of this at its point of inflection. Okay. Determine the equation of the line tangent. We know what to do here. We saw this earlier. We need a point, which is going to be the point of inflection. We haven't found that yet. We need a slope. Okay, the point we'll get from, well, let's cross that bridge when we get there. And then finally, we've got y minus y1 equals m times x minus 1. This is going to be the template for our equation. All right, so first we need to find that point of inflection. That's going to be our x1, y1. So to find the point of inflection, we need to find the second derivative. So let's go through our derivatives here. Y prime is 3x squared minus 6x. Y double prime is going to be 6x minus 6. This is going to have a subcritical value at 0. Okay, so what we need to do is verify this actually is a point of inflection. Oh, wait, is it at 0 or is it at 1? Hold up. 6x minus 0 equals 0. 6x equals 6. So, no. x is 1. Okay, so if there is a point of inflection, it'll be at x equals 1. Phew, glad I caught that. And so to fill in the sign chart, because we're looking to see if f double prime, if that changes sign, then we have a point of inflection. But if the sign doesn't change and we don't have a point of inflection, we have no answer to this problem. So I'm assuming it will change. But let's see. If I substitute in a number like 0 into y double prime, I'm going to get a negative number. If I substitute a number like 2, I'm going to get a positive number. So sure enough, we do get a change in concavity. F is going to, or y changes from being concave down to concave up when x is 1. So this is going to be 1 is guaranteed to be our x coordinate there. Now to find the y coordinate of that point, we need to take that 1 and we're going to plug it back into the original function. So y equals 1 minus 3 plus 2. 1 minus 3 is negative 2. Plus 2 is 0. So that is going to be our y1. That's going to be the y coordinate of the point of inflection. So our point of inflection is at 1, 0. Now that we know where the point is, we can find the slope. Now we already found y prime, so we don't need to recalculate that. But the slope, our m value, is going to be 3 times, and then the x value, we found that was 1. 1 squared minus 6 times 1. So this is going to be 3 minus 6, which is negative 3. So that's going to be our slope. And so now we can write our equation, y minus 0. And just like we did previously, I'm going to leave that 0 there just so we can see exactly what happened to it. And there is our equation. Number 30. All right, we're nearing the end of our third unit here, and there's 4 units total. So we're almost 3/4 of the way done here. I know this video is getting pretty crazy long, but I'm hoping to keep it under 2 hours. We'll see if I can actually make it. So it says determine the following derivatives. Part A, we've got a triple chain rule problem. What colors did I use before? Yellow, green, and red. Okay, so my outside function is yellow, that's tangent. My inside function is f of x, and then well, actually, that would be the middle. The inside function is 3x. So y prime will be first the derivative of tangent. Okay, so the derivative of tangent is secant squared. So secant squared of f of 3x, okay, times the derivative of f of 3x, which is, well, just f prime of 3x, times the derivative of the 3x, which is 3. So the first derivative from the tangent is right here. The second derivative from the f of x is right here. And the third derivative, not the second and third derivative, but the third part of the chain rule, the second part of the chain rule. The third part of the chain rule is going to be 3. Let me just take a quick look, make sure I didn't make a mistake there, but I think that's okay. I think we're good there. Part B, we've got product rule and chain rule all mixed together. Great stuff. Okay, so y prime, or f prime, the derivative here, we're going to use chain rule here, so we're going to start with the outside function, which is something to the 5th power, so that'll be 5 times that something, to the 4th power times the derivative of the inside. So here I'm actually going to use brackets because I'm going to have a sum due to the product rule. And I want to make sure that I don't miss out on these parentheses, because that will give you the wrong answer if you leave out these parentheses. Okay, so on the inside here, I'm going to run the product rule with my first function being e to the x and my second function being sine x. So the derivative of e to the x, just e to the x. So we have e to the x times sine x plus the derivative of, just e to the x regular times the derivative of sine x, which is cosine x. And so there's your derivative. Okay. We're moving on now to our 4th and final unit, where we talked about implicit differentiation. We did some more advanced transcendental derivatives. We did L'Hopital's rule, some tangent line approximations. I think that's about it, but we'll see if there's anything else. So 31 is asking us to find the derivative when y equals -1. We're going to use implicit differentiation to do that. So yeah, basically what we're going to do is we're going to differentiate both sides. And we're going to differentiate each one of these terms separately. So let's start with the first one. We're going to use product rule. The derivative of x is 1. Derivative of y, so 1 times y squared plus x times the derivative of y squared. Derivative of y squared is going to be 2y times y prime because of the chain rule there. So that's that first section. So now I'm going to differentiate negative 3x, and that's just going to be minus 3. And then now we got, okay, so equals the derivative of y cubed, which would be 3y squared times y prime. So now once you do that implicit differentiation, our goal here is to isolate y prime. We're trying to get that by itself. So we're going to move all the terms that have y prime over to the left and all the ones that don't have y prime over to the right. So I'm actually going to rewrite this term right here as 2xy times y prime. I just think it looks a little nicer that way, minus this term over here, 3y squared y prime. And then finally, this is going to equal, after I move all that stuff to the right-hand side, 3 minus y squared. So let's keep our eyes on the prize here. That y prime is what we're going for. That's the dy dx. That's the derivative. So we're going to factor that out as though it was a GCF. I mean, I guess it is a GCF, or at least part of the GCF. But we're going to basically use the distributive property in reverse is another way to think about it. Okay. Now the last step here is going to be to divide by everything that's in that parentheses. So we get y prime equals 3 minus y squared over 2xy minus 3y squared. And if we're trying to find the slope when y equals negative 1, we need to plug in negative 1 into our y prime. Now notice I've got y's here, but I also have an x in here. And so you might be wondering, where does the x come from? I see the y is going to be negative 1, but we're going to get that x back from the original equation by plugging in this negative 1 and then solving for x. So let's do that over here to the side. So x times negative 1 squared would just be 1 minus 3x equals negative 1 cubed is negative 1. So 1x minus 3x is going to be negative 2x equals negative 1. So here x is 2. No, x is not 2. X is 1/2. X is 1/2. So now we've got the x, we've got the y. So now I can plug in the x as 1/2 right down here, and I've already got the y. So now I can answer my question, which is y prime at the point 1/2 comma negative 1 is equal to 3. Minus y squared. So that'd be minus negative 1 squared over 2 times 1/2. Nope. Oh, yeah. 2 times 1/2 squared. Am I missing something here? Hold up. Oh, wait a minute. Back it up. Okay, I won't have to change too much here, but when I divide it here, for some reason I wrote x squared. That should be xy. Yeah, so that's going to be, we're going to plug in a y there. So that should not be squared. Something did not look right, and I'm glad I caught it. 2 times 1/2 times negative 1 minus 3 times negative 1 squared. Take a step back, make sure I don't like to go back and edit these too much. So I try to catch these mistakes like on the fly. So I think we're good here. So we get 3. Minus 1 is going to be 2 in the numerator. And then down in the denominator, we have 2 times 1/2 is just 1. So we've got negative 1 minus 3 is going to be minus 4. So 2 divided by negative 4 will reduce to negative 1/2. All right, number 32. The table below shows some of the values in a differentiable function some of the values of the differentiable functions f and g and their derivatives. H of x is equal to the composite f of g of x. So use the tangent line to h at x equals 5 to approximate h at 5.1. So let's find that tangent line. let's find the tangent line. We're going to need a point, and we're going to need a slope, and we're going to write that equation in y minus y1 equals m times x minus x1 form. So the point is going to be 5 comma something, right? We've got the x equals 5. And so what we're first going to need to do is evaluate h at 5. So h at 5 is going to be f of g at 5. G of 5 is 4. F of 4 is 6. So yeah, h of 5 is 6. So the y-coordinate of the point should be 6. The slope is going to be the value of h prime at 5. So before we find h prime of 5, let's find h prime. So h prime is going to be, we've got a chain rule here, so f prime of g times g prime. And so if we want the slope at x equals 5, h prime at 5 is going to be f prime of g of 5 times g prime at 5. So we'll just evaluate this one step at a time. G of 5, we can, let me erase all this. G of 5 is going to be 4. And g prime of 5 is going to be 9. F prime of 4 is negative 3. So we have negative 3 times 9 is going to be negative 27. So that should be the slope there. Now we can write our tangent line. It'll be y minus 6 equals negative 27 times x minus 5. And so this is the line we're going to use to approximate h of 5 plus 1. Because 5 plus 1, we don't have enough information to really evaluate that, but we can use this tangent line to get a very close approximation. So we're going to take that 5.1 and we're going to substitute it right here into our tangent line. So we've got y minus 6 equals negative 27 times 5.1 minus 5. So 5.1 minus 5 is going to be 0.1. 1/10 of negative 27 is going to be negative 2.7. If I add 6 to both sides, I'm going to get, what would that be? Oh, that's going to be 3.3. So what we can say then, our final conclusion here, is that h of 5.1 is approximately 3.3. Whew, that is a beast of a problem. Yeah, but there you go. Okay, number 33 says, given that g of 5 is 12 and g prime of 5 is negative 2, find the derivative of this function. Okay, so we got a little bit of chain rule. We also have a little logarithm built in there. So just as a little reminder, when you have log of any base and you want to find the derivative of that, it's going to be 1 over whatever's in those parentheses, so just x, or if you've got chain rule, whatever's there, times the natural log of the base. Now, if you have to do chain rule, you're going to have to multiply by whatever the derivative is of whatever's inside the parentheses. So be aware that that might happen here. So let's find f prime. So here's f. Let's identify f prime. So f prime is going to be 1 over g of x plus 3x times the natural log of 3. Okay, all of that times the derivative of what's inside the parentheses. That would be g prime x plus 3. Don't forget to put parentheses around here. I see that mistake pretty frequently. You got to be very careful with your parentheses. And if you don't like having to worry about that, put it in the numerator, and then you don't have to worry about the parentheses. You can write it like this. In fact, it might be even easier if you write it like this. So just a thought. So there's our derivative for f. And what we need to do is evaluate this at x equals 5. So f prime of 5 is going to be g prime of 5 plus 3. Okay, we're going to get that g prime of 5 from the given information. And then we have g of 5. Again, we'll get that from the given information. Plus 3 times 5 times the natural log of 3. So f prime of 5 is going to be equal to g prime of 5. It says negative 2 plus 3. Negative 2 plus 3 is going to be 1 over g of 5 is 12. So we got 12 plus 15. 12 plus 15 is, oh gosh, what's 12 plus 15? Someone help me out here. 12 plus 27. So we got 27 times the natural log of 3. Yeah, I'm asking for some help, and there's nobody sitting here, so I'm just okay. So anyway, f prime of 5 should be 1 over 27 times the natural log of 3. Number 34. Okay, we got selected values of the function h of x, and some selected values from h prime are shown in the table. If g is equal to the g is equal to the inverse of h. So if that's the case, let me write this out. G prime then, if g is the inverse of h, then g prime is going to be 1 over, no, do we have an f here? Hold up here. H prime of g of x. Okay. What's the value of g prime 7? So g prime 7 is going to be 1 over h prime of g of 7. Okay, so let's evaluate that one step at a time here. G of 7. Now, g is the inverse of h. So if we have a point 3, 7 on h of x, which we can see right here, then on g of x, which is the inverse, we should have a point 7, 3. So g of 7 should be 3. So this is going to be 1 over h prime of 3. And we can see h prime of 3 is 5. So g prime of 7 is going to be 1 over 5. Number 35 is missing. Hang on, let me try to refresh this. All right, we're back. We had a few technical difficulties, but I think I'm ready to move past those now. We've got number 35. The limit as x approaches 0 of natural log of e to the 3x plus x all over x. And here we want to use L'Hopital's rule. And usually you'll want to use L'Hopital's rule anytime you try direct substitution by plugging in the value that x is approaching into x. If you end up getting 0 over 0, this is not something that you can equal. I don't want you to ever say equals 0 over 0. This can never happen and can get you points deducted on the AP test. But if that's what you end up getting, then that's an indicator we want to use L'Hopital's rule that says the value of the limit, if you get an indeterminate form using direct substitution, the value of the limit will be equal to the value of the limit of the derivative of the numerator divided by the derivative of the denominator. So we can differentiate both the numerator and the denominator here separately, and then we can try to use direct substitution. The derivative of the numerator is going to be a lot more complicated to get than the denominator here. The derivative of x is just 1, so let's knock that out first. Then we'll find the derivative of natural log of that whole expression. So we're going to need to use the chain rule. And you start that natural log logarithm by going 1 over, and then the expression that's inside the logarithm. But then you have to use the chain rule and multiply by the derivative of what's inside here. Now, this is going to get a little lengthy here, and you got to make sure to put parentheses. But I'm going to actually skip that, and I'm going to just move whatever I would end up with in those parentheses up to the numerator here. So the derivative of e to the 3x plus x is just e to the 3x using the chain rule times 3 plus 1. So now I can use direct substitution without any problem. E to the 3 times 0 times 3 plus 1 over e to the 3 times 0 plus 0. I'm going to ignore that last divide by 1 because dividing by 1 is not going to change the value of the expression. Notice here, no more limit. Okay, I just want to point that out. And the reason why I stopped writing limit is because I substituted 0 in. As soon as you execute that substitution, you do not write that limit. So e to the 3 times 0 is just going to be 1. So we have 1 times 3 plus 1 over 1 plus 0 That's going to give me 4 over 1, which equals 4. Number 36 will be a similar problem. If we try to use direct substitution, we're going to end up with a indeterminate form of 0 over 0, and that's no good. We're going to have to use L'Hopital's rule again. So we're going to want to differentiate both the numerator and the denominator. The derivative of tangent is secant squared, and we're going to have to use chain rule here and multiply secant squared of ax times the derivative of ax, which is just a. Now at this point I want to substitute 0 in. So I'm not going to write the limit notation. I'm going to replace x with 0 and evaluate this. Now a times 0 is just 0. So really I just need to figure out what secant of 0 is and then square that. Well, one thing you got to remember about secant is that it is defined as the reciprocal of cosine. Okay, so really what I want is cosine of 0. Okay, then I know I can find the reciprocal of that, and then I can evaluate secant. Well, cosine of 0 is just 1, and so secant of 0 is 1, and so we have 1 squared, which is 1. So this is really like 1 times a over 4. And a times 1 is a. Can't really do anything else to simplify that, so this limit's going to equal a over 4. Number 37, given that f of x is the natural log of g of x, so we've got a composite function, right, like an f of g of x situation. Anytime you have this composite function and you need to find the derivative, you're going to use the chain rule. I have a lot of students asking a lot of questions like, when do I use the chain rule? What should I look for to know to use the chain rule? And it's whenever you have that function inside another function. Okay, what else is going on here? They give us g, a value for g, and a value for g prime, and they want us to determine the derivative of f at 4. So the instantaneous rate of change of function f when x is 4. And then specifically calls out that we want to see the derivative of f in terms of x and then evaluate it at 4. So I think that when you read that instructions, make sure you write the general form f prime x and not just jump straight to the final value. We're going to find the derivative of f using that chain rule as first the derivative of natural log, which would be 1 over that inside thing, if it's just x, 1 over x, but 1 over g of x, because g of x is on the inside there, times the derivative of the inside. Now the derivative of g of x is just g prime, although I'm going to write this as g prime x over g prime, of g of x, sorry, g prime x over g of x. Now I can evaluate this at x equals 4. I'm going to have g prime of 4 over g of 4. Both of these two values are given up here. So we can evaluate, we can just plug those right in. G prime of 4 is -2, and g of 4 is 5. So here is the value. This is our f prime of 4. And if we really want to go back and state what f prime of x is, we did do that up here, but we can also write it like this. Number 40, determine the values of a and b for which the following function would be differentiable. This is a question, or at least one similar to this, that gave a lot of students a lot of problems on the last test. And I think it was because they maybe didn't make the connection that being differentiable implies that the function is continuous. What we mean by that is that we have two pieces of this function, and not only do these two pieces match up on the graph, who knows what they actually look like, I don't really care about that, but we need those two pieces to meet up at x equals 2, okay, if they're continuous. If they're differentiable, that means the derivative exists, and that means that the slopes are going to sort of approach each other as we approach that x value. And so you have a nice smooth curve, right? No sharp turns or anything like that. Okay, so let's see what we can establish if we're going to assume that the function is both continuous and differentiable. Because the function's continuous, we can say that these two pieces should have the same y value when x is 2. In other words, both functions have the same output at that number. That way we know that the left-hand limit equals the right-hand limit and that those two values equal the value of the function. So ax squared plus 2x plus b needs to be equal to 3ax minus 8. But not generally speaking. They just need to be equal when x is 2. So what I'm going to do here is I'm going to substitute these x's for 2's. And now I'm going to simplify this equation. Okay, 2 squared, that's 4. So you get 4a plus 4 plus b equals 6a minus 8. I'm going to try to pull my variables to the left and my constants to the right. So I got 4a minus 6a is negative 2a plus b. And then I've got negative 8 minus 4 is negative 12. So this is one relationship between a and b that we can establish just based on the fact that it's continuous. And just remember, we know it's continuous because it's differentiable. Now that is not a biconditional statement, meaning that just because a function is continuous doesn't necessarily mean it's differentiable. For example, if you have absolute value of x and you have a sharp turn, this is an example of a continuous function where the left and right hand pieces are equal, but not differentiable. And it's not differentiable because the derivative does not exist here. It's undefined. And part of that has to do with when we differentiate this and find the slopes of those two things, we need the slope of the first piece to be equal to the slope of the second piece. That's really what makes it differentiable. So let's set those two derivatives, which are the equations that represent the slope, equal to each other. So 2ax plus 2 should equal 3a. Yeah, just 3a. But just like with the continuity argument, with differentiability, we really are only checking that it's differentiable at 2. We don't need to check the rest of it. This first function is a quadratic and the second is a linear. We know those are going to be differentiable everywhere they're defined. We don't want the x there is essentially what I'm getting at. We want to replace that x with 2. We really are just checking and making sure that the piecewise function is differentiable at that point where you potentially have a discontinuity. So we can simplify this equation and we get 4a plus 2 equals 3a. I'm going to rearrange this a little bit to solve for a. So I'll subtract 3a on both sides. I'll just be left with a. And then subtract 2 on both sides to get negative 2. Now here I have established that a is negative 2. That's part of my answer here. Going back to what the original question was, and I know this is a long one, but we're looking for a and b. So we know a, and we know a relationship between a and b from the continuity of the function. So we can use substitution to solve for that b. Negative 2 times negative 2 plus b equals negative 12. So 4 plus b is negative 12, and so b is negative 16. So now we've got a, we've got b, we've solved the problem. Really just to reflect back on how we work through this, because it's differentiable, we can say it's continuous. Okay, and once that's established, we're going to make sure that the function's both continuous and differentiable at this particular x value. So to make sure it's continuous there, we set the two pieces equal to each other at that x value. And then to make sure it's differentiable at x equals 2, we set the derivatives equal to each other at that x value. From there, it's just a matter of solving for the parameters are the A and the B, the unknowns. Now, what might happen sometimes is we actually get an equation here. Let's say we got something like 3a plus 2b equals 10 or something like that, where you have two variables in both of these equations. If that were to happen, you'd have to set up a system of equations and solve it using substitution. So this one worked out a little easier because one of the equations gave us one of the constants there. But if we had another linear relationship, then we'd have to solve it using a system of equations. Let's move on. I spent way too much time on that problem. 38. If the position of an object is given by p of x equals arctangent of 2 of x, determine the acceleration of the object at x equals 3. I made this note before, I think, but just, we don't need that compass there. I made this point before, but when you're given on these position, velocity, acceleration problems, there's a couple of things that I want you to just be ready for every time you come up to one of these. First is the position function is not always p. Sometimes it's x, like in terms of t. Sometimes it's s in terms of t. I've seen it called all kinds of things. Maybe d, distance sometimes. Usually it's t. In this case, it's x. Our independent variable is. But the position, for whatever reason, there's not really like a consensus for what the position function should be called. So it might be called just whatever, and you just have to roll with it. Now, with velocity acceleration, those are pretty universally going to be v and a, usually of t, but in this case, x. But those two names for the functions are usually pretty consistent, being v and a. So that's the first thing. It's just like recognizing that the position function could be called anything else, and I don't want that to confuse you. That like if you see this named something weird. The second thing is about the relationship between position, velocity, and acceleration. And this is something that you can make sure to get the points on the AP test if you do this right away, and that is to just cite the relationship between the two. So in this case, we have the function p of x. That's our position. The velocity will be the derivative of the position. The acceleration will be the derivative of the velocity, or you can say that it's the second derivative of the position. So if you establish this fact up front, you can make sure that you get the point on the AP test. No matter what it's asking for, if you just like get in the habit of just like throwing this down on your free response problem, if it's a position, velocity, acceleration problem, you can rest assured that you're going to get that point. Because and this is something we talked about in class. There was a problem where we were trying to find the velocity, or I don't remember exactly, but we were given the position, and the way I had worked it originally is I just kind of assumed we would know that the velocity was the derivative of the position. But if I didn't write that, if I just kind of, like in this case, if I just go and find the velocity equation, which is we know is the derivative of arctangent, but let's say your transcendental derivatives and your chain rule, and you get this right, and you say, okay, well that's 2 over 1 plus 2x squared. All right, it'd be like 1 over 1 plus 2x squared times times the derivative of 2x, which is 2. Let's say you knew that and you got that right. You could still potentially lose a point by not establishing the connection between p and v here. So that's something that's really easy to overlook, and I just really want to point that out, that you really want to make a statement like this, at least somewhere. It doesn't have to be like inside your work necessarily, but if it's relevant to the problem you're working on, if you have to make that connection between the velocity and the position, you've got to write it out like that. So we could say that like here, the derivative of the position is equal to the velocity, which is equal to this expression. And this is really probably the best way you can say that. You can say this up front, just to like make sure you get the points. But if you're just trying to be efficient about what you're writing, you could just write it like this. So anyway, okay, so that's the position function, and now that's velocity. Now let's get the acceleration. So the acceleration, right, is the second derivative of the position, or you can think of it as the first derivative of the velocity. That is acceleration. And so what we need to do is we need to differentiate this using this using the quotient rule. So derivative of 2 is just 0. So 0 times, no, I got that. 0 times 1 plus 4x squared. Okay, if you were going to simplify this, the denominator, you could write that as 4x squared, minus 2, which is the numerator, times the derivative of the denominator, which would be 8x. And that's a good reason why you should probably rewrite it like that. It just makes finding that derivative a little easier when you write it in that standard form. Okay, all of that divided by the denominator squared. So this is just going to be 1 plus 4x squared, quantity squared. And I'm not going to bother multiplying that out or trying to simplify that because I'm just going to be substituting a number in anyway. Going back to the original problem, we have the position of an object given by this arctangent function. We're trying to determine the acceleration at x equals 3. So now we've got that equation for acceleration. Now we can evaluate it when x is 3. So we're just going to plug in 3 into every instance of x here. So what do we have? We've got if 3 squared is 9. Oh, wait, hang on here. This is all times 0. So I don't really need to evaluate that first one. So I'm going to skip past that. It's going to be negative 2 times 8 times 3 divided by 1 plus 4. And I'll just go ahead and do the x squared times 9 squared. So negative 2 times 8, that's negative 16, times 3 is negative 48. This bottom one, though, I think it's going to be just kind of a little unreasonable to do without a calculator. We got 37 squared. I'm happy if you just write it like that. Normally, also on something like a question like this, you'd be asked to give the units, which there were no units given in this problem, so it's not like you can just guess. But usually with these position, velocity, acceleration problems, the position is typically given in meters. It's like some distance. The velocity could be any distance, but usually any distance per time, I should say. The velocity usually is in meters per second. The acceleration is usually in meters per second squared. Not always. It could be feet per minute and feet per minute squared and all that kind of stuff. But that's typically what it is. And if you were given units originally, you'd have to write them here. But there's no units given, so we're just going to leave it as a numerical value. And if you just really want to see what you're not going to be able to use a calculator, but I'm going to cheat here and do 37 times 37 here on the calculator. And just if you're curious, you got the right answer here, negative 48 over 1,369. But I wouldn't expect you to make that leap. And on the midterm, you're not going to be able to have to do arithmetic like that. Okay, let's wrap this up. We're on the last page. Number 39 says determine the points in the curve. And then we're given this equation that does not have y isolated. So it looks like we're probably going to have to use implicit differentiation here. Where there are horizontal tangent lines, so the slope, or y prime, is going to be 0 here. So we're looking for the points where there are horizontal tangent lines. Okay, then write the equations of the horizontal tangent lines. So when we're writing the equations of horizontal, normally when we write equations of tangent lines, we write them as y minus y1 equals m times x minus x1. But if we know they're horizontal, those are just going to be y equals, and then a number here. It'd actually be the y-intercept, so it would be the y-coordinate, right, the y1. And that's because we know the slope is 0. The slope is the m in this equation. Okay, if that's 0, then yeah, it's just going to be. So anyway, the horizontal equations are just going to be y equals a certain number. So I just want to point that out there. So what we need to find is that point. So we're going to have to figure out where is the slope equal to 0. So to find that slope, we need to be able to find y prime. And to find y prime, we need to use implicit differentiation. So we're going to differentiate both sides of this equation, the left-hand side and the right-hand side. The derivative of the left-hand side is going to be 2y and then times y prime due to the chain rule. Recall that the derivative of y is, in terms of x, is 1 times the derivative of y. I'm not really writing that very well, am I? There we go. Another way to think about it is if we're trying to find the derivative of a function that's not x but is in terms of x. Okay, then we need to find. Well, this isn't probably going to be a good example either. Let's say. Well, yeah, I'll just run with it. So the derivative of f of x is just going to be f prime of x times the derivative of x. Yeah, and the derivative of x is just 1. But if this are y, so it's a function y, it's going to be equal to that the derivative of that function. Yeah. Okay, anyway, let's move on here. So we've got 2y, y prime, minus 2 times x, minus 6 equals 0. And then we're trying to solve for y prime here. So we're going to add the 2x and the 6 to the right-hand side, and then divide everything by 2y. Now, if we want to find where, that should be a y, not a 6. If we want to find the points where the tangent line is horizontal, that's when y prime is 0. So we need to set this expression equal to 0. Multiplying by both sides by 2y is going to give me 2x plus 6 equals 0. And then I can subtract 6 and then divide by 2 to get negative 3. So negative 3 is going to be the x-coordinate of the point where we have a horizontal tangent line. Now, because of the nature of the original equation, we have a y squared in there. It's possible we get 2 coordinates. And, I wouldn't try to remember how many coordinates you could get. What you want to do is just plug that back into the original equation and solve for y, and however many solutions you get, that's how many coordinates there will be. So let's plug that back in. We got this x equals negative 3. We are going to substitute that back into x. So I'll do that over here to the left. Y squared minus negative 3 squared minus 6x equals 10. So y squared minus 9. Oh, and then I didn't substitute in the negative 3. Plus 18 equals 10. So y squared equals, 10 plus 9 is going to be 19. 19 minus 18 will be 1. So y is going to be plus or minus 1. Okay, so that means we've got a total of 2 coordinates. We've got, a coordinate where we've got negative 3 comma 1, and another one where we have negative 3 comma negative 1. All right, sorry I had a little interruption there, but yeah, our 2 coordinates are going to be negative 3 positive 1 and negative 3 negative 1. Number 41, absolute extrema. So this was, we just had a very brief lesson right after our last test where we talked about absolute extrema and how to use the candidates test. Struggling there with the spelling. Okay, the candidates test to determine absolute extrema. So basically what you want to do is you want to set up a table of values with the endpoints of the interval you're interested in and any other critical values. Okay, so we need to find the critical values, which are the values of x that make the derivative equal 0. So find that derivative. Let's find these critical values. The derivative of f of x is going to be 3x squared plus 6x, and we want to set that equal to 0. 3 times 2 is 6. Nope. Nope. What am I doing? We're sorry, got distracted there. We're going to factor out 3x and multiply that by x plus 2. So now we could set each one of these equal to 0, and we get x equals 0 and x equals -2. These are the critical values of the function f. These are points where you potentially have a local extreme value, either a max or a min. Now, we know that just because they're critical values, though, they're not guaranteed to be a maximum or minimum. You might have a case where you just have a horizontal tangent line, something like this, where the slope doesn't change from negative to positive or vice versa. In this case, it would still be a critical value, but would not represent a local extreme. But nevertheless, it's not really worth the time and effort to determine if these are local extremes. It's easier just to go ahead and just, throw them into your table. Maybe I should put them in order. Find the value of the function at each of these x values and just figure out which one is the smallest. Okay, in this case, we're looking for the absolute minimum, which is why we're looking for the smallest f of x value. If it said absolute maximum, we'd look for the biggest one. So we got our critical values, we have our endpoints, and we need to consider the value for f of x at all of these. So this is probably one of the most tedious kinds of questions out there because you just have to brute force your way through these. You got to do the arithmetic, and you have to figure out what the value of the function at each of these x values are. So let's start with -4. F of -4 is going to be -4 cubed plus 3 times -4 squared plus 7. So let's see here. We got 16 times 3. So that's going to be -9. F of -2 is going to be -2 cubed. That's -8 plus 3 times -2 squared. 7. So we got 4 plus 7. That's going to be 11. If we substitute in 0, 0 cubed, this would be the easiest one, is 0. Plus 3 times 0 is still 0. Plus 7 is 7. And then lastly, we're going to find f of 2. So we'll substitute in 2 here. So we get 8. Nope, I need that squared there, don't I? We got 8, and then we get 4 times, that's 12, so that's 20, plus 7 is going to be 27. Okay, so we've got our table filled out, and we're looking for the absolute minimum. So we're looking for the smallest value of f, and we can see that's going to be -9. So we have our absolute minimum at the endpoint -4, where x is -4, and the value of the absolute minimum is -9. So to answer this question, really what we want to say here is that, well, let's not say it with the highlighter there. The absolute minimum value of f on the interval -4 to 2 is -9. And a lot of times when it asks you to justify your answer or give a reason for your answer, 9 times out of 10, it's going to be something along the lines of like, oh, because f prime is positive, or f double prime is negative, or f goes from negative to positive, or something like that. Basically, it's looking for the sign of f prime or f double prime, but not always. In this case, you don't have to really make a separate statement to justify your answer. Your justification is the table of values you made. So this table that we made right here, that right there, that's your justification. So the table is the justification. Justification. There we go. So you don't have to make a separate statement. Your answer is that the absolute minimum is -9, and the justification is just showing your work going through the table and basically verifying that that is the smallest value. Okay, that brings us to our very last problem, and it looks like it's a two-parter here, of course. Why not? And we're just trying to find y prime. Okay, kind of the theme of the whole semester is learning how to differentiate, what differentiation means, what it can represent, just in real life, and also give you some just like really crazy abstract equations that we can now find functions that represent their slopes at any point. So that's just kind of cool that you could do that, which is like these really complicated ones. So part A is just going to be, just a run through some of these newer transcendental derivatives like 4 to the x, mixed in with some old transcendental trigonometric derivatives like cosecant. Got some chain rule, got a cotangent in there. We got all kinds of stuff. So we'll start with the first one. And I think what I'll do here is just run through this. So this is going to require the chain rule. Okay, if I just have 4 to the x, and I want to find the derivative of that, that would be 4 to the x times the natural log of 4. But I don't just have 4 to the x times the natural log of 4. I have 4 to the cotangent x, so I have to use chain rule. So I am going to have, I'm going to need some more room here. I am going to have that 4 to the cotangent x times the natural log of 4, right? Just from doing the regular old exponential derivative. But I do need to multiply that by the derivative of that exponent, the cotangent x. And the derivative of cotangent is going to be negative cosecant squared x. So that is all from the first piece. And then, well, maybe I'll do the second piece in a different color here. So the second piece is the derivative of cosecant 4x. Now, the derivative of cosecant is negative cosecant times cotangent, but we are going to have to use chain rule here. So I actually do not want a plus there. I want a minus because it is negative cosecant of 4x times cotangent of 4x times the derivative of 4x, which is 4. I'm not going to bother differentiate or simplifying this any further. I'm going to just leave that as it is. I kind of like how crazy it looks. If I were to do anything, I might bring this negative out to the front here just for aesthetic purposes. But otherwise, I'm pretty happy with how that looks. Okay, we got our very last problem of the review, and it's an implicit differentiation problem because y is not isolated here. So we're trying to find y prime. We're going to have to use the chain rule on this cosine y. Get negative sine y times y prime. The derivative of x squared is 2x. The derivative of y is y prime. The derivative of 3x cubed is 9x squared. And so now we're going to try to isolate y prime. So I'm going to leave the y primes on one side. I'm actually just going to kind of do this in 2 steps since we've done quite a bit of implicit differentiation so far, and this is the last problem. I think we can handle it. I'm going to do the factoring along with it. So y prime times 1 minus sine y equals 9x squared, and then I'm going to bring that 2x over to the right-hand side because I really just want everything that doesn't have y prime on the other side. So my last step is going to be to divide both sides by 1 minus sine y. So y prime is 9x squared minus 2x over 1 minus sine y. And that is going to close us out. This has been quite a long midterm review, and I appreciate you doing all the hard work that you do on your end. I mean, you've made it quite a long way. At this point, you have a firm grasp on limits and derivatives, and that's going to set you up really well for next semester. So just whatever you do, just do your best, and that's going to be good enough. That's going to get you to where you want to be. Anyway, as always, if you have any questions, please reach out to me via email, come see me in the morning, or just comment underneath the video, and I'll get back to you no matter how you try to get out to me, and to try to help you out on any of these problems. So you guys have a great evening. Yeah, I'll see you next time.